This is how fast GPS satellites move. It's wild. If a GPS satellite flies at 2.02 miles per second, does that mean it slows to 1,037 miles per hour? Short answer, no. That mixes two different speeds and two different reference frames. Hook first, 1 to 37 miles per hour is how fast the Earth spins at the equator. A GPS satellite, though, orbits way faster, around 2.4 miles per second, which is about 8,600 miles per hour. If you use 2.02 miles per second, that's still roughly 7,300 miles per hour. So what happens in 7 seconds? Multiply 2.02 miles per second by 7. That's about 14 miles traveled, not 1,037 miles per hour. Hours and seconds aren't interchangeable. Per second is an instantaneous rate. Per hour is the same rate scaled by 3,600. Here's the clear picture. Earth's surface at the equator, about 1,037 miles per hour east. GPS satellite, about 8,600 miles per hour relative to Earth's center. Over 7 seconds at 2.02 miles per second, about 14 miles along its orbit. So where does slowing really show up? In the clocks. Because of Einstein, motion makes time tick slower, and being higher in weaker gravity makes it tick faster. For GPS, the velocity effect slows the onboard clock by about 7 microseconds per day. Gravity speeds it up by about 45 microseconds per day. Net, the satellite clock runs faster by around 38 microseconds per day. That tiny mismatch would wreck your phone's location if we didn't pre-correct it. The satellites are intentionally offset, so, from Earth, their time matches ours. Bottom line, 2.02 miles per second doesn't become 1,037 miles per hour, and 7 seconds of travel is about 14 miles, not a speed. The only real slowing that matters for GPS is in the clock math, and that's exactly what makes your maps work. Wild, right? Satellites don't outrun Earth, they orbit it. Here's a quick way to think about wider area trajectory. If I stand on the equator, Earth carries me about 1,040 miles per hour, but a low Earth orbit satellite zips along much faster, around 17,000 miles per hour. So yeah, about 16 times faster. But speed isn't the same as how wide the path is. A satellite can go way faster and still trace a tight curve around Earth, because gravity is constantly bending its path. That curve is the orbit. Let me make it concrete with a 10-minute thought experiment. In 10 minutes, the satellite covers about 7.8 kilometers per second, times 600 seconds. Call it 4,680 kilometers along its orbit. Meanwhile, the equator moves at about 465 meters per second. So in 10 minutes, Earth's surface carries me roughly 279 kilometers. Same time window, the satellite's path length is about 16.8 times bigger. Now the geometry, path length s equals radius r times angle θ. For a typical LEO at about 400 kilometers altitude, r is roughly Earth's radius plus 400 kilometers, about 6,771 kilometers. In those 10 minutes, s is about 4,680 kilometers, so SR 0.69 radians, around 40 degrees. Earth's rotation in 10 minutes is about 2.5 degrees, so the satellite sweeps a much bigger angular arc than the ground under it. If you're thinking, couldn't GPS just show the bigger displacement? Yes, that's exactly what it measures in an Earth-fixed frame. But the satellite's true path is a curved orbit, not a straight line.